Hi everyone, our topic is addressing the Stadler problem in iterative convergent parallel machine learning. And our presenters are Harshavardhan, Bhanuvarma, and Akhil. These are the authors of our paper. The introduction to Stadler problem is Stadlers are slow nodes in distributed computing environment that delay overall task completion. Impact on machine learning is slows down convergence in iterative algorithms, reduces resource efficiency, and increases runtime. The importance is understanding and mitigating Stagler issues is crucial for optimizing performance in parallel machine learning tasks. This they can arise due to various factors, including hardware variability, network latency, and data skew. Consequences of Staglers in machine learning are extended computation time. The overall training time increases, leading to inefficiencies. Poor model performances in our inconsistent iterations can affect model accuracy and convergence. Resource wastage or idle resources while waiting for stragglers can lead to increased operational cost. User frustration, no longer wait times for results can hinder research and deployment cycles. Impact on machine learning, the presence of stragglers can significantly impact the convergence rate and accuracy of machine learning models. This can lead to increased training time and resource wastage, ultimately affecting the model's performance in real-world applications. Stragglers to mitigate task scheduling use dynamic scheduling to allocate resources based on current load. Speculative execution. It is duplicate tasks on faster nodes to ensure timely completion. Introduction Flexor. Flexor is a novel solution to mitigate the Stagler problem in iterative data parallel machine learning workflows. Here are some key points to introduce Flexor. Flexor is runtime solution designed to address delays caused by stragglers in distributed machine learning systems. It combines state synchronous parallel bounds with a dynamic work reassignment mechanism called rapid reassignment. Key features of Flexor are flexible synchronization, which allows faster workers to proceed within a defined slack limit without waiting for slower ones, which ensures system efficiency and convergence. Dynamic work redistribution. Slower workers can offload portions of their workload to faster peers dynamically. The core components are stale synchronous parallel for flexible synchronization. Architecture is peer-to-peer communication among workers. Parameter server to manage shared state. Benefits of Flexor mitigates stagglers, reduces idle time caused by transient or persistent slowdowns in workers, ensures the entire system is not held by the slowest thread. Scalable and adaptable, adapts to both real-world and synthetic straggler patterns, works well across different machine learning applications. Near ideal performances achieve significant runtime like BSP and SSP.
This is Akhil. I'm now going to conclude this way. Then, role of now we are going to see the role of state synchronous parallel. State synchronous parallel is a key component in the flexor addressing the synchronous problems in the distributed solution. Workers ahead. Workers will head up for the slack bond and continue without waiting. What workers can do without waiting of any other blockages and ensures the performance of efficiency, which makes the performance more efficiency. And SSP remains the mathematical guarantees for the machine learning algorithms for the coverage of dispute minor delays, so that the work efficiency is more and making that FlexRR work efficiently and getting the more results, reducing the communication overhead and frequent in the barrier synchronization enables FlexRR to handle larger clusters more efficiently with the workloads and efficiency. Rapid reassignment is the one of the key program in the what we call rapid reassignment is one of the key thing for the Flexara, which what we call which detect the slack curve as soon as the peer for the progress report within the workers, redistribution the partitions and the slow down the workload up to the faster levels of workers. Users help a group minimize the data and mounted communication overhead. Employees by activating and temporary reassignment and assurance to the efficiency. Maintain system progress by pretending the ideal time and reducing the delays, so that the system time will be increased and delays also decreased. Helpers growth in the what we call helpers growth in the rapid reassignment. Each worker is being assigned for the work, and helper group workers are eligible to assist, and helping group workers that are current node may be not assist. A helpers group reduce the communication overhead by limiting the iterations, and data perfecting ensures the faster work on overhead handovers, work faster and handovers. SSP in the SSP like system SSP in the Flex or implementation, workers process tasks asynchronously within the defined Slack bond, updates the delays in corrected with the consistency graphs, reduces the side synchronization overhead the BSP, improving the efficiency and increasing the what we call increasing the quality of the thing, ensures the coverages with the minor discombination in the parameters and the updates. Second, uh, scalability in the distributed systems. It has it is in the distributed systems in the which are not centralized, which are decentralized. Decentralized contribution. Flexor has the peer-to-peer communication, eliminating the benefits associated with the centralized controllers, so that the work efficiency is more efficient. Work reassignment helpers in the groups, which are enabled the localized reassignment and minimizing the data movement and reducing the network overhead. Availability of the cluster sizes so that our performance is effectively both small and the clusters and the large scale cloud infrastructures, and EC, which are, for example, like EC2 and Azure. We can see there are some clusters which are centralized. We can see them availability. If there is availability, we will as soon as there is an availability, we can use them and ensure that quality of their work. Handles heterogeneous environments, adapts the variable workers to spread the controls and multi-talented systems. Overhead in the large workloads. When if it is a workload is heavy, the ideal time should be very less and maintains that near ideal time, and what we call less ideal time, and increasing the iterations on the task or the nodes. Now we can see the real stragglers and the synthetic stragglers, the differences between the real stragglers and the synthetic stragglers. Real stragglers are naturally occurring shadows in the real world environment like cloud and infrastructure. Artificial stragglers are like injected delays and the examples created for control for testing and the evaluation. Naturally occurring stragglers, resource continuation and the multiple tendency. Indexing stragglers flow the workers and power on the distribution. Real patterns are validated in the practical availability in the cloud and distributed environments. Synthetic patterns are highlighted in this availability and diverse in them. Now we will go with the overall view. Flexor continuously reduced the titration of 35 to 56 percentage in the BSP in the, under the relevant regulations. Overall, Flexor provide benefit and efficiency in the efficient resolution in the migrating smuggler problems. So and making the system to work without being idle and making the better environment for that. Now we are going with the experimental setup. It will be continued by Mr. Har.
The experimental set of key points tested on diverse platforms including Amazon EC2 and Microsoft Azure and local clusters. Configuration ranged from small instances to large ones. Experiments included both real-world experiments and synthetic strangler scenarios. Evaluated Flex RR against BSP, SSP, and ideal performance baselines. Used injected to delay stimulate transient and persistent strangler effects. Applications tested. Matrix factorization MF, recommended systems for collaborating filters. Logistic regression, multi-class classification tasks in machine learning models. Latent direct performance on Amazon EC. Flexara achieved 35 to 53% reduction in time per iteration compared to BSP, demonstrated significant improvements even under transient strangler effects, consistently outperformed SSP with up to 39% faster iterations. Large benefits observed on small instances with higher contention, maintained near ideal performance across real and synthetic strangler scenarios. Similar results observed on Azure A3 and A4 instances. FlexRR consistently reduced iteration time by up to 56%. Over BSP works well even under frequent unpredicted delays in multi-tenant systems. Impact on convergence. FlexRR ensures fast convergence by reducing iteration time without sacrificing accuracy. Requires slightly more iteration in extreme strangler scenarios, but still achieves faster overall convergence. Matrix factorization converges 10% faster than BSP, even with injected delays. Minimal increase in convergence time under strangler pattern maintain model accuracy. The trade-off between convergence time and iteration count is minor, ensuring efficient performance. FlexRR maintains near ideal performance, preventing strangler effect caused by uneven task allocation. FlexRR reduces delays by 54% in experiments. Sensitivity analysis. Tested FlexRR performance across various parameter settings. Helper group size, work assignment size, and message check frequency. Helper group size. Optimal performance achieved with 4 or more helpers. Working assignment size. Small initial assignments followed by larger follow-ups ensure efficient workload distribution. Message check frequency. Frequency between 100 and 10,000 checks per iteration perform well, minimizing overhead. Sensitivity test confirm that FlexRR perform consistently across a wide range of parameter configuration. Comparison with alternatives. BSP. Strict synchronization insufficient under stranglers. SSP. Reduces delay but limited by slack bonds. FlexRR combines SSP flexibility with rapid reassignment to handle larger delays. Example, improvement up to 10 times faster BSP under extreme synthetic delays. Conclusion. FlexRR successfully mitigates the strangler problems in distributed iterative machine learning, combines SSP for flexible synchronization with rapid reassignment for dynamic workload redistribution, demonstrates significant performance improvements up to 53% over BSP and SSP under real and synthetic strangler conditions. Scalable and adaptable to large cloud infrastructure and diverse machine learning tasks. Ensuring near ideal runtimes, making it practical solution for large-scale distributed machine learning. Future works include exploring adaptive slacks, bounds, and expanding FlexRR to integrate more machine learning frameworks. Thank you. Now, now addressing the questions asked for the paper presentation. What is the novel contribution or solution proposed in this paper? To address this question about the novel contribution or solution proposed in the paper on addressing the strangler problem for iterative convergent parallel machine learning ML as well as its significance and originality, here is a structured response. Novel contribution. Proposed solution. The paper likely introduces a specific algorithm or framework designed to identify and mitigate the effects of strangler during the iterative process of parallel machine learning. This could involve adaptive task scheduling, dynamically reallocating tasks based on the real-time performance metrics, speculative execution, running duplicate tasks on faster nodes to ensure time completion, load balance techniques, improving data partitioning to prevent uneven workloads among nodes, feedback mechanisms, implementing real-time monitoring and feedback system to adaptively manage resources. Significance of contribution. Significance. If the proposed solution effectively reduces the impact of strangler, it can significant it can significantly enhance the efficiency and speed of parallel machine learning training. This is particularly important in applications that require iterative learning, such as deep learning and large-scale data analysis. The ability to achieve fast convergence while maintaining model accuracy is crucial moment in the field. Originality. Blazing versus incremental. The originality of contribution can be accessed based on how it compares to existing methods. Trailblazing. If the solution introduces a fundamentally new approach or framework that has not been previously explored, it can be considered trailblazing. Incremental. If it builds on techniques with moderate improvements or optimization, it may be classified as incremental but valuable for advancing the state of the art. Now, remaining questions are explained by my teammate Akhil.
Yeah. Now we are going to see the problems, remaining questions like which are the problem addressed in this paper. In this paper, it is the problem of iterative conjugation and iterative conjugation in the machine learning algorithms, which is main affecting for the time of the algorithm, which is affecting mainly for the time and moreover efficiency of the work. And for this, we can see that there is an what we call what important problem is it is impact it is affecting a lot in the real time world, as it is a very big problem. It is when we are going to with the when we are going with the huge data, which makes the theory which make the admission not work for few money, and what we call and which is making the solution delayed solution, and which may be giving the chance for the other people or other solutions for the effective solution, and which we are mainly losing the opportunity for that for clearing the problem of the solution, or clearing some good content, good chance for that, and sometimes even the chance of doing the things and making the system like making the some of the people idle, so that the efficiency of the algorithm is also be reduced. And now the second question, we are having the what is are there any solutions for this problem? Yes, we are proposing the like in this paper it is proposing the solution of flex error is the best solution for this problem. As it is reassigning the work, it is not making the workers sitting idle without any work, as it is setting the things, and when it is making the it's not making the complete ideal, it is not removing completely ideal, but yeah, it is making someone at least there is some work which is decreasing the ideal time of the workers and the machine learning theories, so that the work efficiency will be increased, and making that solution in the efficient way and the best time way, effective way and best time way, because by saving the time and power of the energy resources, and so that we can find the solution for that. Author demonstrate How did the authors demonstrate that solution to the workers? The third question, like fourth question we are having is the authors demonstrated the solution for the workers. I can say that the author has demonstrated the workers. Yes, it is in a perfect way, as the authors directly show the solution, directly see the problem which we are lacking of, and making them what we call the perfect example for the solution, by showing the rapid relation problem, and see that there are some many things like rapid reassignment and SSP. We can see rapid reassignment and SSP. There are some alternatives for them also. They have shown the analysis even for this problem. Author has given perfectly the reasoning for this author, by all these terms, and we can say that author has given all the perfectly terms for this one. And remaining questions is answered by my friend Banu.
Achieve what they set out to do. The key goals stated by the authors are addresses the straggler problems, which is mitigate delays caused by slow workers in distributed iterative machine learning system. Propose a novel solution. Combines stale synchronous parallel with rapid reassignment to reduce idle time and improve performance. Ensure practical effectiveness. Validate the solution through experiments on real-world platforms like Amazon EC2 and Microsoft Azure. Demonstrate scalability. Prove Lexar's applicability across diverse workloads, cluster sizes, and stagger scenarios. Is the paper well organized and presented? Yes, the paper is well organized and effectively presented. Here is our assessment, which is clear structure. The paper follows a logical flow like introduction, problem definition, related work, methodology, experiments, result, and conclusion. Each section builds on the previous one, making it easy to follow. Detailed problem definition. The straggler problem is well explained within real world examples and its impact on distributed machine learning systems. Innovative solution. The authors present Flexar with detailed design elements like SSP and rapid reassignment, making the solutions novelty and practicality clear. Complementive, comprehensive experiments. Extensive testing on real-world platforms such as Microsoft Azure, EC2, and synthetic setups demonstrate the system's robustness. And the last question, which is, what did we learn from this paper? This paper provides valuable insights into addressing performance challenges in distributed iterative machine learning systems. Here are our key takeaways from this paper, which is the Stagler problem in distributed machine learning. Stagglers are slow performing workers cause significant delays in synchronized distributed systems. Its causes include hardware variability, resource contention, background processes, and uneven workload distribution. Traditional synchronization models like bulk synchronous parallel amplify the impact of stagglers. Scalability in distributed systems. Lexar performs well in both small and large clusters, adapting to heterogeneous environments, handling uneven workload distribution, maintaining system performance even under imbalanced conditions. Experimentation and validation. The use of both real-world synthetic straggler patterns ensures a robust evaluation. Lexar outperforms alternatives across a wide range of scenarios, demonstrating its practical applicability. Novel solution Lexar. Lexar combines tail synchronous parallel for flexible synchronization, and it works efficiently across variable workloads, including matrix factorization, logistic regression, and LDA. This is our presentation. Thank you.